Boom.
Good morning, ladies and gentlemen. Sorry, now it's getting a little running here. Okay, so do this now. This is a little bit of review. If you don't know it, look in your notes. What is work?
Yep.
And what are the units of work? Lastly, what is the work energy theorem?
So take a few minutes, stop the video, see if you can find this information, and then we'll get rolling. All right.
You find it? Okay, so hopefully you've got that work is force over the force you exert on something over a displacement,
Yep.
right?
And the equation is force times displacement
Yeah.
in the direction of the work.
Well, the force is the displacement is in the direction of the force, right?
Yep.
What are the units of work? Okay, so should I do this on the board?
You could, sure.
So work equals force times displacement, where the displacement is in the direction of the force. That means they're just like, same direction,
Yep.
right? And then what are the units? Well, this is a Newton and this is a meter. So it could be a Newton meter,
Yep.
or we could call it a
Joule.
joule, okay?
Our friend the Joule.
And then what is the work energy theorem? Well, it looks something like this. Work changes energy.
That's all there is to it.
If you put work into something, you're going to change the amount of energy that it has.
Yep. It's a simple yet profound idea.
Yeah, so let's keep on moving through here. You lift a 7.5 kilogram bowling ball. Here's this guy right here. Okay, we'll start him on the ground. Okay, you lift a 7.5 kilogram bowling ball 0.91 meters from the floor to the table. Okay, here's our table. Okay, I lift him up. I put him here. Okay, put him here. How much work did I just do?
I know.
How much work did I do? Okay, well, this is work. Our definition for work, right?
How can you find the force?
Well, our force.
What are you doing work against?
Oh, I'm doing work against gravity.
That's right.
So wait, at the very top, it's gonna be all UG, right?
Well, one thing at a time. We find the
Okay,
work
okay.
first.
All right, so work is force times displacement, and my force was this way because I was doing force
Yeah.
against gravity, and my displacement is that way, right?
Yeah.
Okay. Well, how do I find what's my equation for force?
It's mass times the acceleration due to gravity.
Yeah. Okay, so I'm actually just gonna put that in here. So
I
I'm
like
saying
that.
work equals m times g, right? That goes right there.
Yeah.
Times my displacement. Okay. And what was my mass? 7.5.
7.5 kilograms.
Okay, and my gravity is, we're doing work against gravity, so it's positive. Okay, and I multiply it by my displacement, which is 0.91 meters. Okay, guys, go ahead and plug. This is our
No, it's okay.
He's like, take the calculator. 7.5 times 9.8 times 0.91. And I get, we'll call it 67.
67 Newton meters.
Or
67 joules.
Okay.
Simple, you guys remember doing this?
Yeah, you guys remember, right?
Yep.
And this is just like our UG equation, right?
Yep.
Okay, because everything's been transferred to. Okay. What happened to the work you did?
Well, it's in the bowling ball.
So it's stored at the top here as potential energy.
Gravitational potential energy, absolutely.
Yeah. The work that I did, the amount of work that I did pulling it up here, work changes the amount of energy it has. Now it has a whole bunch of UG,
Yep.
right? And let's keep going. If the floor is 0, how much gravitational potential energy UG does the ball have?
Well, the work energy theorem is going to answer that question for
Yeah,
us.
well, we just said that work equals the change in energy, and if our work is 67 joules right here, what our change in energy, this is also equal to UG, right?
Yeah, because if the
Okay.
floor is 0, it had no potential energy down there.
That means that this is our UG.
Yep.
Yeah, so, all of the work that we do to lift that ball up, it gets transformed into potential energy, and it's stored in the ball, 67 joules, just waiting to fall to the ground.
I can't see it there, but it could fall off that thing onto the floor.
You never know. Okay. Next question. Does Earth have a gravitational field?
What is a field?
What is a field? A field is just an area of space that things happen, right?
Yep. Well, in this particular case, where a force can be exerted.
Where a force can be exerted, yes.
Yeah.
I'm thinking about like a soccer field.
Right.
Where
Baseball
things
field.
happen.
Yeah.
Yeah, where a force can be exerted. And do we experience forces that keep us on this lovely planet?
That's why Mr. Boykin was ever able to dunk the basketball.
Yeah. So the answer is yes. Yes, we do. So we absolutely experience a force. Earth does have a gravitational field.
Yep.
Okay. So how did we change Coulomb's law into this? You know what, I'm gonna do this over here.
I remember the zombie hand
Zombie hand.
from the video.
Like what video? Go back and rewatch it, people. I'm telling you. Okay, so let's see. We start off with
What's
this.
Coulomb's law look like?
Okay, Coulomb's law looks like this. So we've got K, Q test prime over d squared.
Sure. Could be r squared, d
It
squared.
could be r squared. I know. I was like, what do I do?
Yep.
Okay, so how do we change it into that? Okay.
Well, the zombie hand came in and grabbed.
And I took this and I put it right there. I gotta give myself a little more right here.
Yeah.
Okay, picks this up and puts it right here. Go ahead and erase it from right here.
Yeah, and make that the electrical force while you're at it.
Oh yeah. Okay, so this right
This,
here.
this right here.
Oh, thank you. Yeah. Okay, and then this right here. What is this? That's the same thing as this, right? Isn't it? What is this? The
That was-
electric field just is.
Yeah, that was the
Right?
existential electric field.
Yeah. Oh no, wrong thing. Sorry. This more can't talk and write.
Well, it's pretty early in the morning.
Yeah. So we just took this and we're gonna put it right here. So instead of having all these things, I'm gonna go ahead and erase this. No, keep it there.
Yeah, keep that
Oh, yeah, right.
there.
Oh. Okay, Q prime d squared. Okay. Whew, my arm is getting tied up there. Should I rewrite? Oh no, you guys
Just
see
leave
up
it
there.
alone. Let's go to the next
Yeah,
thing.
yeah. And so that E, and so do you guys see how this is this? Okay, we just took that a little bit in the front with our zombie hand, and that E is there.
Yep.
Okay. Do the same thing to Newton's law of universal gravitation. Do you guys remember this?
Yep.
Right? We've got that G, that constant, that gravitational constant. This is that first mass, the second mass, this is how far apart they are.
Yep.
Okay. So let's do the same thing. The force of, that's why we had that G there. Okay, so I'm gonna go ahead and give myself a little more room here.
There you go.
Okay, so G, M1, M2 all over D squared. Okay, so same thing. I'm gonna take that M2 right here and I'm gonna zombie hand it and put it up here.
And instead of M1, make that the mass of the Earth.
Earth right
There
there.
you go.
Right, because we're talking about the Earth and some satellite orbiting it. It's Earth is
So
that
just
thing.
like, because these two equations are of the same form and they come out of the inverse square law, there's an interesting thing about this. Do you guys remember what it is? Or do we have to go to the next slide?
Let's go to the next slide. Okay. So let's figure out what this right here. Oh, and you know, there's a d squared. It's the same thing, r squared.
Yeah.
Let's figure out what this what number
Well,
this represents.
On top, you've got the electric field is equal to this. So this would be the gravitational field.
Now, do I write it as E still?
No,
or?
It's the gravitational field. Let's just go to the next slide here.
All right, let's
See,
see
because
if
the
we
Earth
can-
has a gravitational field too.
Yeah. Okay. So let's go ahead and find this. So G. Let's figure out G mass of the Earth over d squared. Okay. So that's gonna be 6.67 times 10 to the negative 11th Newton meters squared over kilogram squared. Wow, those units are really similar to these ones.
Yeah.
Okay. Times the mass of the Earth, 5.98 times 10 to the 24th kilograms, divided by the radius of the Earth, 6.38 times 10 to the 6 meters. Oh, squared.
Don't forget to square it.
Don't forget to square it. Okay, let's go ahead and plug this in. So I've got 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th divided by 6.38 times 10 to the 6th, and I have to square that bottom part. You see that right? Okay.
No,
And
but
I
that's
get,
okay.
what do I get? About 9.8.
9.80.
Okay, so this equals 9.80.
meters per second squared.
Uh-huh.
And
Meters per
so
second squared.
the E, capital E, is the electric field, and the gravitational field intensity would be lowercase g. So that's the gravitational field.
Lowercase g, you said? Oh, FMG.
Yep. Nope.
Yeah.
Nope. Just lowercase g. That's the. So the acceleration due to gravity here on the surface of the Earth is the result of the intensity of Earth's gravitational field.
Yeah.
And if you went farther away from Earth, it would get smaller.
Oh.
Yep.
Now we've seen this like this, right?
Yep.
Right there? Okay.
Which is the same thing that we've done right here.
Yeah, so this is just little g. And this is just a big E. And what does it represent again? It's the
Field.
the field, right? And it represents the intensity of that gravitational field.
Yep.
Just like this represents the intensity of our electric field. Okay. Whew, that is some cool stuff. Good there? We finished that?
Yep.
Okay. Doing work on a mass in a gravitational field can change its gravitational potential energy.
Got this bowling ball up here off the floor. It has gravitational potential energy because you did work on it.
Yeah, and that's just a fancy word for our UG, right?
Well, yeah, UG is the symbol for gravitational potential energy.
Yeah, in case you forgot.
I mean, that's a lot of syllables right there.
Who wants to write all that, right? So doing work on a mass in a gravitational field like we have here can change its gravitational potential energy, its UG. Okay, yes, we know this. How would you change the potential energy of a test charge in an electric field?
Well,
Well, I'd probably
fields are
move it.
fields are fields.
Yeah. So couldn't I just move it around, right? If I have an electric field coming around this originating charge, and this is where it's at. If I wanted to change the potential energy of a test charge, can't I just move it?
That's right. And when you do work on it, let's say, and when you move it, you apply a force through displacement, you're doing work.
Okay, so
I
basically
think that's the next
do work.
slide.
Let's see what it says there. So work is force times displacement. We know this changes the electric potential energy. We're gonna call it the EPE because again, who's got time to write all that? Of the moving charge. So if I do work on a charge, it changes the electric potential energy.
Yep.
Okay. Very similar to the gravitational potential energy.
Yep.
It's electric. Okay. All right. So let's go ahead and dive into this next section. A capacitor. Let's take a look at a capacitor. Write that down. Get your words in. Like get your steps in, get your words in. Okay. All right, ladies and gentlemen. So this is a capacitor. A capacitor has two metal plates on each side.
Take that apart. It's two pie plates.
Two pie plates, and get a little hungry. Two metal pie plates with opposite charges. Now we're going to talk about how or why it gets those metal charges.
How can-
those positives.
Dun dun.
Da 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 da. Do you want to do this first?
Right
or-
now.
Okay. All right. So I'm going to go ahead and hook this up.
This is our Wimshurst machine that pumps electrons from one side to the other. And when you connect it with wires to one pie plate and then the other pie plate, it'll pump electrons from one side to the other.
Okay. So I'm going to go ahead and start turning this thing up here. Okay. Are these good right here?
Yeah, should be. All right, so and you notice you have to slowly increase it.
Yeah. Ooh, it started to move a little bit.
All right. So now she's pumping electrons from one side to the other, and you can prove it with that screwdriver.
Oh, it's
No.
being lame. Wait, can I keep going here? There we go. So what's happening there? Electrons are jumping from the top to the bottom, yeah?
That's right, because you've got a whole bunch. Here, go ahead and
Ah, there we go. Okay, I'm gonna go ahead and those
Yeah,
guys.
this thing will bite you if you're not careful.
Okay, and so what's happened for Mr. Boykin in the past is that there's actually been a jump from here to here without the help of our screwdriver.
It all depends on the humidity.
Some days better than others. So today needs a little bit of help.
So let's make the diagram.
Yeah, so what is going on here? Okay.
So how do you make one positive and one negative?
How do we make the top, because we said the top side becomes positive and the
Well,
bottom,
what
one
happens
side
if you
becomes
take an
positive.
electron?
So an electron, what we do is one electron is going to jump from here down to this bottom side here.
That's what this thing was doing. It was taking electrons from one side and putting it on the other.
And before, they were neutral, right?
Yeah.
But when an electron goes from here to here, now this side at the bottom becomes negative because it has that one extra electron,
A
right?
little bit of negative, yeah.
Okay, and then this one becomes positive.
A little bit of positive.
Okay, now again, an electron jumps from here to here. That's that spark.
Well,
that
it's
we
not
see.
jumping. No,
Okay.
you're pumping it with this thing right here. You're removing electrons from one side and putting them on the other.
Okay, we're pumping it. Okay. Okay, and again, we pump in another electron over here. Boop, boop, and that makes this side have get another positive.
Because for every electron you take off the top makes it positive. You put that electron on the bottom makes it negative.
And what happens is that is how we get this these opposite charges on each plate.
And what we had is a bunch of positive charge on one side, bunch of negative charge on the other one. And when you put the screwdriver close, the electrons jumped from the negative charge side to the positive charge. Why? Well, you got a bunch of electrons. They find them repulsive. And there's a bunch of naked protons. They find them attractive. So they jump back through the air.
So we have these charged plates now. And what if I have we're gonna call this our 1 Coulomb charge.
Okay.
Okay,
You
this
have
is
a
our test
positive test charge.
Yeah, positive. And what would happen if I put it into this capacitor right here?
Well, if it's positive, what kind of forces is, okay, it'll be attracted to the negative, but it'll also be repelled from the positive.
Yeah, it's repelled from the positive, attracted from the negative, and it's gonna kind of zip down here.
Right.
Right? Okay. All right, so we've got our 1 Coulomb charge in there. That's what it looks like. Let's talk about what's going on inside of here. So we have a uniform electric field that exists between the parallel plates.
Yeah, if you've got a force exerted on a test charge, there must be an electric field.
Yeah, right, and we just said that
And
this
since the positive test charge, it's going to be away from the positive and toward the negative, away from the positive toward the negative, away from the positive towards the negative, away from the positive towards the negative.
right, equally distanced apart because the uniform, what is when you say uniform?
Well, it's like sports teams. How can you tell which team is which?
You're all wearing the same uniform, right?
That's it.
And so a uniform, our uniform electric field is the same throughout, evenly spaced. It all looks the same. Okay.
And there's a picture in the book on
yeah,
page 490. You've got 2 charged plates, and you can see the electric field in between them runs from one side to the other, just like the diagram we've got.
Okay, so let's take a look at a practice problem here. So it says a capacitor has plates 0.1 meter apart. Okay.
So the electric field is 5 newtons per coulomb. I think that should be.
Inside. Okay.
No,
so,
put that right next to, make it the same color as your arrows.
Absolutely. Okay, so electric field, what we say, 5 Newton coulombs?
5 newtons per coulomb.
Newton per coulomb. Okay. So we said it's how long? It's point.
Well, that doesn't matter right now. We can get to that in a minute.
That's not M. It's D, right?
So how much force would be exerted on a 1 coulomb charge?
Okay, so we've got our 1 Coulomb charge coming in here.
First of all, how would you solve that electric field equation?
Okay. Well, we've got the Coulomb and we've got the E.
E
Okay.
equals, well, wait a minute. Yeah, the electric field is F over Q prime.
I'm like that, okay? And what are we trying to find here?
Force.
How much force? Okay, so let's go ahead and
If
put
you
this.
solve that for force,
looks like this. Okay, I'm gonna go ahead and make this look a little bit better. Check this out. What is this one, Mr. Boykin?
Earthquake!
This is earthquake. Okay, so if we want to figure out the force of a test charge in an electric field, we use our earthquake equation.
That's right, E times
right?
Q.
Hey, you know what? I'm actually gonna make this E purple like this. Okay.
All right.
All right. So let's go ahead and plug this in. So our our electric field is 5 newton coulombs, right?
Yeah.
And what did we say our test charge was?
1 coulomb.
Okay, I wish I had that orange pen we talked about before, but it is what it is. I'll use this guy. Ooh, this is kind of dirty. Times 1 coulomb.
Yep.
Okay, and
5 times 1, boys and
is
girls. You need a
5.
calculator.
5 newtons here, because our C's cancel out.
Yeah. 5 newtons. So the force would be 5 newtons.
Okay.
What if you had more charge? What would that do? If
Okay,
you
this
had-
was a 1. This was a positive 1. What if I bring in my 2 coulomb charge? Da-da-da-da. Okay, so well, let's talk about what happens first. First of all, same thing.
repelled from the positive, attracted to the negative.
Yeah. Okay. But let's go ahead and take a look at this. So we're gonna calculate our new force, like how much force
Yeah.
is exerted on this charge. Okay. So I'm gonna do it. Okay. So we'll do right here. Force equals earthquake. Okay. And earthquake. So that gets me 5 newton coulombs. And what's my charge here?
2 coulombs.
2 coulombs, okay? So times 2 coulombs, and that gets me
10 newtons.
10 newtons. Okay, so it looks like
The field is the same,
field is the same.
but the force depends on how much charge you put in
Ooh,
there.
that's important. The force depends on how much charge.
Yep.
I'm gonna write myself that over here. Force depends on the charge. Cool?
Okay. How much work to move it from one side? Well, if you throw the charge in there, where's it going to go?
Okay, so if I throw it in here, right here, now I gotta.
You got to do
Okay.
work because it doesn't want to be up there by that positive.
Yeah, so how do we find the work here for this?
What is that equation for work?
Well, work equals force times displacement, right?
Yep.
Okay. And what was our force?
Well, for the 5 newtons,
Okay.
and the displacement is 0.1 meters.
Okay, so that's going to be just 0.5, right?
0.5 joules.
Joules. Okay, so it takes me 0.5 joules of work to do it for my one
What about if you had the 2 coulomb?
Okay, well, I'm gonna do that over here. So work equals force times displacement. My force here is 10 newtons. My displacement is
0.1 meters.
0.1 still, right?
Yeah.
Okay, that's gonna be 1, right?
Yep.
Okay, 1 joule of work.
So how much work depends on how much force. It's like lifting a heavier bowling ball.
Okay, and how much force depends on how much charge.
That's right.
Okay, so the work also depends on the charge. Is that fair?
Yep.
Okay, so the force depends on the charge and the work. Okay, so this is starting to make sense. So it's all about the charge here. Okay.
Yeah.
All right. Let me make sure I covered all my bases here. Yes. Okay. So since how much work depends on how much charge. We got that here. Since how much work depends on how much charge.
Yeah.
A ratio of work to charge is most useful.
So that'd be W over Q prime.
Yeah, okay, so work to charge. I'll do that right here. So work to the test charge, right? What was our work for this one over here?
Well, you got it right there. It's half a joule.
It's half a joule, so 0.5 joules divided by,
And how much charge? That was the 1 coulomb,
it was
wasn't
a
it?
1 coulomb, right, yeah. Let me use my green here. Okay, I wish I had like the pink. I should use the pink and the different colors here, but that's
You
okay.
need to go to the stove.
I know, I need to go to Costco, okay? And then that just gives me
0.5 joules per coulomb.
coulomb, okay?
What about for the 2 joule? I mean the 2 coulomb charge.
Okay, so we're still doing work over the charge, right? So
Yeah, what's that ratio going to be?
So 1 joule divided by my charge, which is, in this case, it's 2 coulombs, right?
Yep.
Okay, so 1 divided by 2, that is
0.5. And that's the same thing we got before. So it doesn't, and what you're talking about here is the properties of the capacitor.
Okay.
The properties of the capacitor are there whether you have the charge or not.
Whether it's there or not, baby.
And so this is an important idea. So we follow what we got here. We got an electric field that was formed by moving electrons from one plate to the other.
Okay.
And then you put a charge inside there, a force is exerted on it. And if you move it from one side to the other, you have to do work.
Mm-hmm.
But a ratio of the work to the charge is going to be the same, half a joule per coulomb, half a joule per coulomb.
So, and you said, I think this is really important, this number right here is a property of the field.
Yep, the property of the field inside the capacitor.
Okay. All right, so electric potential difference.
Boys and girls, here's today's big idea. We've been doing all this tap dancing just to get to this right now.
Okay, so we said the work over the test charge is the most useful. 'Cause it
How do we
gives us
get,
that
yeah,
ratio.
and how do we get the work?
Well, we did the force times the displacement here.
Yep.
And we said earlier, I'm gonna go back, I actually forgot we had the slide here before, but this one right here, the work changes the electric potential energy.
Of the moving charge.
Okay, so right here we've got work changes electric potential energy. We just put that in there.
So that's
we
a
talked
work
about that
energy
definition.
theorem
Yeah.
applied to, and that's called, when you take that change in energy divided by how much charge moving around,
Does this look familiar? This is
the electric potential difference, it's delta V.
delta V, okay?
What
The
are-
electric potential difference.
Okay, what are the units of this going to be?
Well, joules per coulomb, otherwise known as the volt.
The volt,
The
our friend the
volt.
volt. And everybody knows what a volt, or has heard of a volt. Now you know what a volt is. It's how much work is done moving a charge inside an electric field, divided by how much charge you're moving around.
That's nicely put. Okay. Let's see. You do 5 joules of work moving a 1 coulomb charge from the negative to the positive. What does the delta be? I'm gonna go ahead and erase this, yeah?
All right.
You guys go ahead and get started on this. We'll write down our equation.
Don't.
Oh.
That's okay.
I'll leave that part up there.
That diagram is a valuable thing
Okay.
right there.
We still have, no, this one here. I'll trace it back up there. All right, you guys, keep doing your thing. Miss Moore is recovering her partially erased diagram. 1, 2, 3, 4, 5. All right. 1, 2, 3, 4.
I don't think you're going to need a calculator for this one. If you do 5 joules of work moving 1 coulomb of charge from the negative to the positive plate of a capacitor, what's the potential difference between the plates? Well, that's just going to be the work divided by the charge, isn't
Yeah,
it?
you guys ready for this? Okay, so we want to figure out our electrical potential difference here. We just said it's the work over the charge, right?
Yep.
Okay, and what do we have up there? We've got the work, which is 5 joules, right?
And we've got the charge.
Which is just plus 1 coulomb. Okay, so our electrical potential difference is just
5 joules per coulomb, or
5
5 volts.
or 5 volts. There we go. I've got green all over my hand. Okay, or 5 volts. Bada boom. Okay. Sweet. Okay, so since force over displacement divided by the test charge is equal to the electrical potential difference, and since this is equal to this right here is equal to that.
Wait a minute. That bottom. Do you see that bottom in the top?
Okay, so they're the same, right? Right? If I just cover that.
Oh yeah. So you
Okay.
could substitute that E, and ladies and gentlemen,
I just put it up there. So E times
gives us
D. Ed. Okay, so in a uniform electric field, the electrical potential difference is equal to the electric field times the displacement, or Ed.
Yep. And there's several ways you can think of this. It's how far you move a charge inside that field, but it's also how far apart the plates are. So
Oh,
depending
okay.
on the situation, you can use it in different
Yeah,
things.
so-
For example, that last one, what was it? 5 newtons per coulomb was the electric field.
Oh, yeah, before, yeah.
And how far apart were the plates?
0.1 meters.
So how could we find the potential difference?
Oh, we just multiply it. 5 times 0.1.
Yeah,
Yeah, okay. And you get 0.5, and that's what we got.
that's
from
what we
all the
had
other-
before.
Yeah, 0.5. Okay, I see it. All right, so let's do a practice problem here. So 2 parallel plates with opposite charges, like we have over here, measure an electric potential difference of 60 volts.
60 volts.
Okay, so we're gonna say
Delta V is 60 volts.
if the plates are 0.03 meters apart, what is the intensity of the electric field inside?
So what was that equation we're dealing with?
We're talking about Ed.
Ed.
Okay.
How do you solve that for E?
We're just gonna divide by D.
That's all.
Yeah. Okay, so 60 volts divided by 0.03 meters. 60 divided by 0.03. Bada boom. 60 divided by 0.03, and I get 2,000.
2,000.
2,000.
And what are the units of the electric field?
The electric field is newtons coulombs.
Yep.
Cool. Okay. So this is making sense. All that hard work for Ed.
That's right.
Thanks, Ed. Okay. What does each symbol represent?
Take a moment, boys and girls. What is each? You can't play the game unless you know to play it.
All right. So here we go. D for displacement. E for electric field.
Yep.
This is our test charge.
Yep.
Force. Work. And electric potential difference.
Yep.
Now, are kids sometimes tempted to call this the change in voltage?
Well, what'll happen is electrical potential difference is a lot of syllables.
Yeah.
And eventually you'll end up saying potential difference.
Mm-hmm.
And then you'll end up saying potential. And then you'll end up saying voltage. But it's electrical potential difference or voltage or electrical potential. We'll play with this more as we go along.
Okay, I'm just curious. 2 charged parallel plates are 0.04 meters apart with an electric field intensity of 625 newtons.
Should we let them do this?
Yeah, go ahead and do this one.
Because isn't this the last slide?
It is. Actually, let's have them do this for homework.
Here's,
Or should we do it with them?
well, you can do it with them in class. So
Okay,
see what you can do with this, boys and girls.
We'll come back to it tomorrow.
All right.